Algebra 2, Chapter 5, Section 5, Modeling with Linear Functions and Equations. A linear model can be used to model various kinds of data sets when the data resembles a line. Now, this may not even be a precise match. For instance, we might have a data set with points like this, and we might model this data with a line. A data set can be determined to be linear by examining the rate of change for entries in the data, or the table for the data. If the rate of change is roughly the same everywhere, a linear model will work well. So if we were to examine the rates of change of these points, we would find that they're roughly the same if we average them. The same rate of change can be easily identified when the table is in regularly spaced intervals, as the change in the value would be constant. So if we have a table with regular spaced intervals, 1, 2, 3, 4, 5, 6, and we have the output values always have the same change each time, this is linear. And we can identify that quickly by this pattern. So let's practice. Is the temperature in this table linear with respect to depth? If so, find a formula for temperature as a function of depth, for depths ranging from 150 to 300 meters. This is temperature of water at a depth inside of the ocean, say. Well, let's look. So we have 150, 175. Let's write the change in depth here between each two cells. 25, 25, 25, 25, 25, 25. So each change in the sort of input in our independent variable is 25 meters. So now let's look at the change in temperature between each cell. This looks like 0.25 degrees Celsius, 0.25, 0.25, 0.25, 0.25, and 0.25. So they are all the same. Is the temperature in the table linear with respect to depth? Yes. Find a formula h as a function of depth d for the ranges in here. So to do this, we can do our point slope form. So our slope would be the change in the output, or the change in the dependent variable over the change in the independent variable, delta y over delta x. Basically, each one of these changes is the same because it's linear, 0.25 over 25, which is the same as 1/100th. If we multiply by 4, you have 1 on the top and you have 100 in the bottom, or 0.1. That's our slope. So we can write an equation, h equals slope m, which is 0.01, oops, 1/100th, 0.01 times, remember the form of point slope form was m x minus x naught plus y naught, where x naught, y naught's our point. So here our x is actually called d, our independent variable, or our input placeholder x. Our x naught could be any point on this graph. Let's just take 150 since it's the first, and our y naught. And now we have a linear model. So our answer is yes to the first part, and our model is given by this function. Maybe we need to box that better. And it says a function, so let's write that as a function notation. H of d is this. So let's look at these tables. Which of the following tables could represent a linear function? Let's quickly check the spacing's the same. Yeah, they're all 5 each time for the input, both tables. So in the output here we have -3, -3, -3. So yes, this is linear. Here we have -3. This is the same table. Some kind of mistake in the slides here. Let's pretend the table looks like this. 17, 9, 5, and 2. So here we would have a change of -8, -4, and -3. So this is not linear. So there was a mistake in the slides here. Sorry about that. But this point is easily to observe. We just need to check the distances apart and see if the change in y over the change in x, which is the rate of change, is the same everywhere. If it's the same everywhere, it is linear. If it's not, it's not linear. Now let's talk a little bit about a constraint equation and do an example. A constraint equation is one that constrains some model. So this model, we're going to talk about a motel. So a newly designed motel has S small rooms, which measure 250 square feet, and L large rooms, which measure 400 square feet. The designers have 10,000 square feet of available space for rooms. Write an equation relating S and L and graph the result. Here's where you'll see standard form be quite useful. So we have 10,000 square feet of space, and we have some small rooms, and we have some large rooms. So a small room takes up 250 square feet. So the number of small rooms times 250 will be the square footage that we use for small rooms. And the large rooms take 400 square feet. So 400 times L will be the space it takes for a large room. Adding them together gives us our total space, which has to be less than or equal to 10,000 for us to have a valid design. So this is a constraint inequality, and we can write an equation which is where the constraint is exactly met by just changing this to an equation. This will tell us when we have the most possible rooms. So we can have an inequality which has to be true, and then we can analyze the boundary of the constraint using this equation. Okay, so write an equation, we did that, and graph. This is an equation if we use all the space, and graph the result. Okay, so graph the result. Let's make some axes. So if we think about this equation, standard form does give us access to the intercepts fairly easily. So if we think about, this is the small axis and this is the large room axis. If we think about what happens if we have no small rooms, we would have, this goes away if there's no small rooms, and we would have 400 times the large rooms is 10,000. So the large rooms would be 10,000 over 400, which is 25. So when there's no small rooms, we have 25 large rooms. And if there's no large rooms, we have 250 S is 10,000. S would be 10,000 over 250. We're left with 1,000 divided by 25, which would be 20. Because, no, 20 is not right, 40. So we can verify this with a calculator just to be sure. 10,000 divided by 250 is 40, yes. because 40 times 25 is 1,000. So 40 small rooms with no large rooms. And we know this is a linear equation. There'll be a line joining these 2 points. Now we can just use a ruler to draw our line connecting these points, and we have a graph. Now what's interesting is the area under this graph can represent all the possible valid configurations for our motel. Because we have, this is the actual constraint inequality, we just need to have our points that are possibilities of large rooms and small rooms need to be smaller than or equal to this line of constraints. And of course we can't have a negative number of large or small rooms. So this area here beneath this line that we've drawn or graphed represents all the possible configurations which are valid. And this is a common layout for constraints. Now you may have more constraints which could draw more lines or more even non-lines. Say you have a constraint for some reason like this, and that would erase this area under the curve, and we would know which parts, which configurations are valid for large and small rooms. So let's go back and think a little bit more about this example. What if the plans now call for a total floor space of 16,000 square feet? So there's a change. Find a new constraint equation. So the new one, instead of 10,000, we have 16,000. 250 small plus 400 large equals 16,000. Okay, that was easy. Find the new constraint. Done. Sketch its graph together with the original. So let's go back and sketch the new graph. First we need to think about how many more rooms we can have. So now we have, when there's no small rooms, we have large is 16,000 over 400, which is 40 large. And for small, we have 16,000 over 250, which would be, let's use a calculator, 1,600 divided by 25, 64. So we would have 40 large rooms and 64 small. So let's make a new graph on our new page. Our original graph we had for small and large, we had 40, 25, when we had 10,000 square feet to deal with. This is our original equation, the original line. So now we have, use red, 40, so here's 20 roughly, double that's roughly here, 40, and we have 64, 20, 40, 64 small rooms. So by having 16,000 square feet, we have moved the line up, representing the new amount of space. We now have more possible configurations that are valid. So here we have the large rooms. Could be up to 40 with no small rooms with a new constraint of 16,000 square feet. Or we could be anywhere on this line or anywhere in between and still be valid with this constraint.